So we are all PL researchers here, and what we do is we study programs and programming languages. An important part of what we do is actually proving correctness of programs for whatever notion of correctness that is. And for this purpose, we use mathematical tools. We define the semantics of our programming languages and programs, for example, the operational semantics, and state theorems about programs and programming languages using these semantics. And we use our mathematical tools and techniques to prove those properties, right? One of the important tools in our toolbox is program logics. And this is what I'm going to talk about today, specifically about the iris program logic. A program logic is a formal system, a formal and foundational system that basically gives us a language for expressing the properties that we want to prove our programs, and also gives us a way to achieve that, to prove those properties. So let's see some interesting properties. One thing that we want to prove about our programs is that they don't crash, right? The safety property, I guess the bare minimum of what we want to prove about our programs is that they don't crash. And we define this mathematically using operational semantics like this. I guess most of you should be familiar with this, but anyway, we are using here a smallest of operational semantics, and this is how I write it, with an arrow saying that there is one step of computation from E prime to E second. We say that the program E is safe if whenever we run the program for some number of steps and reach some other program E prime, then we have either reached a value, the computation has finished, or we can still continue the computation, right?
I mean, I'm sorry to interrupt. I have two questions.
Yes.
The first is, I only see your first slide, and I wonder if other people are in the same boat, or I assume you have changed your slide, but I only see the first one.
Yes, I have.
Yes, I only can see the first one too.
And
okay.
My second question was, would you prefer people to interrupt with questions if they have some, or would you like to get the questions at the end? Yes, now I see the new slide. Thank you, and sorry for the trouble.
Well, let's see. I guess you can ask questions, but well, we have to also manage the time. So let's see. All right. So as I was saying, in this model, the way we actually model crashing in this formalism is programs that actually are not a value and also cannot be executed any further. So let's look at a couple of examples. For example, this program here is a program consisting of a loop, a recursive function f that immediately makes a call to itself, which is a loop, and we call it. This is a non-terminating program. If we run this program, it never terminates. And well, it is nonetheless safe, right? Because if we run it for a number of steps, we never reach a value, but we can still continue executing the program. But this program is not safe. This is not a value, and we also don't know how to continue executing this program, right? Here in the condition we expect a Boolean, but we have a string. Do you see the next slide now?
Yes.
Okay, good. Another interesting property that we might want to prove about our programs is functional correctness or partial functional correctness. And that is saying that not only that the program does not crash, but there is a certain post condition for our program that whenever we run the program and we get a value at the end, then that value should satisfy some post condition phi, right? So for example, we can say that the program 3 plus 5 is correct with respect to the post condition that says that the value should be even, right? Another interesting property is the type safety property, which says that if a program is well typed, then it will not crash. Indeed, the example that we have here has a typing problem. Here we expect a Boolean, but we have a string, right? And the type safety theorem says that any program that crashes must have some typing problem, or in other words, all programs that pass the type checker will not crash. In this talk, I will tell you about Iris and how we use Iris to prove such properties. But before that, what is Iris? One way that I can explain what Iris is that using this diagram, showing you that there is a logic that we call the base logic of Iris. This is a logic that is designed for specifying program logics, for constructing ways to prove properties about programs. And with Iris, we have a built-in program logic that is built on top of this base logic and the operational semantics. So the idea is that you can define your own programming language and give its operational semantics to Iris, and what you get is a program logic for your programming language, and then you can use that. But then you might ask, what does it mean if we prove that a program is correct in Iris? Well, the adequacy theorem of Iris, as we'll see, tells us that if we prove that a program is correct in Iris, then we get the functional correctness property or safety that we just saw. And that is a property that is only in terms of the operational semantics, right? So what you get is that if you prove that something is correct in in Iris, you get a proof of correctness in Coq. So you don't have to trust Iris, you don't have to know anything about Iris if you're just focusing on the end results. It may also be that for the properties that you want to prove, for the kind of programs that you're interested in, the built-in program logic of Iris is not strong enough for you. And we can handle that. You can define your own custom program logic, as we have done in these works for reasoning about the esteem monad, for example, or non-interference properties. The built-in logic of Iris was not strong enough, and the authors had to define their own program logic. But why Iris? Why is Iris interesting? Iris is interesting because it is very useful. It has been applied to many, many different projects, from verifying session types to reasoning about hardware machines, security properties, reasoning about distributed systems, gradual typing, effect handlers, weak memory properties, the language theoretic properties of the dot programming language, the core calculus of the Scala language, the properties of the Rust type system. And there are many examples. And the reason for this versatility is Iris's expressivity. And that's what I'm going to talk about. So let me briefly mention what the base logic of Iris actually gives us. I will get into the details of these things later on, but just for now, let me just give you the high-level view. First and foremost, Iris is a higher order logic. And what I mean by that is that apart from the ordinary logical connectives, you have universal and existential quantifiers in Iris that basically you can use to quantify over anything, including the Iris propositions and predicates themselves. That's the higher order aspect of the logic. Iris is also a separation logic, meaning that all propositions in Iris assert or can assert some ownership of some resource. What that means, we will see. And we have here the quintessential connective of the separation logic, the separating conjunction, which says that two things hold for disjoint resources. Also, Iris allows users to define their own resources, not just the resource that corresponds to the memory that is usual in separation logics, as you will see, but also user-defined resources, which allow us to define theories to reason about our programs. And we write it like this, saying that we own resource A under the resource instance gamma. And we also have an update modality that I will explain later, which allows us to update resources in our logic. Iris also features a step indexing and invariance. Step indexing basically what we have is that all propositions in Iris, everything, is tied to the number of steps of execution of the program. And what we have here is the so-called later modality, which says that P holds, but only after you execute the program for one step. And we also can take fixed points of propositions. We can define recursive propositions guarded by later. We will see an example of that. And of course, invariants are very important in Iris. They allow us to express the fact that something holds forever. Okay, before I get back and explain those things in more detail, let me say a bit about the program logic of Iris. The Iris program logic is a Hoare style program logic, meaning that you have these things called Hoare triples. In a Hoare triple, you have a precondition, the program, and the postcondition. And the idea is that whenever the precondition holds, it is safe to run the program. And when and if you get a result out of this program, that result will satisfy the postcondition. For example, we can give the following spec for the factorial function, saying that if the number that we give to the factorial function is non-negative, then the result that we get out is actually the result of the mathematical factorial function. And also for the looping program that we saw, well, we can specify it like so, saying that, well, this is always safe. It doesn't require any precondition. And the postcondition that it satisfies is false, meaning that whenever the program terminates, we should have false, meaning that the program never terminates. As I said, the adequacy theorem of Iris tells us that if we prove something in Iris, prove that the program is correct with respect to the precondition true, meaning that if we prove that the program is always correct unconditionally, then we get that the functional correctness property that I mentioned earlier holds for this program with respect to the postcondition that we have. Here I write for a suitable postcondition. The idea is that the postcondition that you have here should basically correspond to the higher order fragment of the logic. It cannot say anything about resources or invariants or things like that. They don't make any sense outside the Iris world. And of course, alongside this notion of Hoare triples, we also get proof rules that tell us how we can use these constructs in our language to prove correctness of programs. Okay, let's see an example of why it is interesting to have higher order logic in your system. Let us think about how we can specify a stack. Our stack has three operations. We can create a stack, we can push onto it, and we can pop from it. And we specify this as a stack using a predicate is a stack that takes a value that is the stack itself and a list of predicates that describe the contents of the stack. Initially, when we create the stack, we get some value s that is an empty stack. And we know that if we have a stack whose contents are described by predicates phi, and we have that phi s, and we have that the value that we are pushing satisfies a predicate phi, then we get afterwards that the value that we get out is the unit value. That's not that important. And what we get is that the contents of the stack are now described by this extended list that has this phi at the top, meaning that the top element of the stack satisfies phi. And also, when we pop an element from the stack, if we know that the top element satisfies some property phi, we are guaranteed to get back a value that satisfies that phi predicate, and we actually get that this stack has changed and we have popped something out of the stack. Now, notice that here we are using a higher order quantification. This stack predicate is a predicate itself that we are quantifying over. but it's also a higher order predicate. It's a predicate that takes predicates as arguments. The idea here is that instead of tracking what are the elements that are in the stack, we are tracking their properties. What are the properties of the elements that we have pushed and popped? And that is more useful for reasoning about the properties of programs. By the way, notice also that the usual specification, if I call it the usual specification of the stacks where we keep track of the list of elements, can be derived from this specification. That is not a bad exercise in logic to do, perhaps. Another important thing is that here notice that by existentially quantifying this is a stack predicate. What we are telling the client, the person who's going to use the stack, is that they don't know how this predicate is instantiated. They don't know what the internals of the stack are, right? We are abstracting over the details of the implementation of the stack and of the proof, right? The only information that we're giving them is that they can use it with the stack operation. Okay, let's go to the separation logic. As I said, we have the separating conjunction in our system, which says that P and Q hold for disjoint resources. Now, what is a predicate that asserts some ownership of resources? Well, the quintessential example is the points to predicate that asserts ownership over memory. This predicate here, L points to V, says that memory location L actually holds a value V, and we have exclusive ownership over this. Meaning that if we have two points to predicates for two locations, we know that those two locations cannot be aliasing. They should be different locations because the resources are disjoint, right? And the logic also tells us how this points to proposition is used. This basically reflects the semantics of the program that you expect. When we allocate a reference, we get the exclusive ownership of the reference that we allocated. And when we want to read a memory location, we should have the ownership, we should have the permission, so to speak, to read that location. And the value that we get is exactly what we expect, and we still have afterwards the ownership of the location. And also, if we own the location, we can write to it, and we get that the location is updated. The resources are updated to reflect how we have updated the memory. Now, why is separation logic interesting? One of the important features of separation logic is that whole triples in separation logic specify a kind of footprint of the program. They basically tell you what part of memory or what resources the program is going to work with. This is captured in this frame rule, which says that if we know a whole triple for a program, and we have some resources that are disjoint from the resources that the program uses, if we have those resources before running the program, we also have those resources afterwards, meaning that the program cannot tamper with any of those resources. This is quite crucial because it tells us that if we have two parts of the program that work on disjoint parts of memory, then we can reason about those parts separately. We can prove them correct separately and then compose the proofs. We know that they're not going to tamper with one another. But what about the parts of the program that actually share memory? Well, in that case, as we will see an example, we will have to use invariants and resources to specify how those parts of the program that share the memory should interact with the memory so that they work together and don't corrupt the memory for other parts. Apart from the points to propositions, which are which were traditionally the only resources that we had in separation logic. In Iris and in most modern separation logics, users can define their own resources. And they do this by defining a structure called a partial commutative monoid. We don't want to get into that here. The key point is that the user gets to control how resources are combined and what it means for resources to be disjoint. It is happening by this equation in our system, which says that owning A and B separately is the same as owning A combined with B, where the combination is defined by the user. So the user gets to control how the predicates that are defined based on user defined resources behave and interact with one another. And we also have the update modality in our logic, which basically says that P may not hold right now, but it will hold after updating resources. It is useful, and you will see it, but the point is that our program logic is defined in such a way that at any point during the proof, we can update resources. The high-level idea is that we are going to verify stateful programs that have memory. So we have to reason about the way that a state is used in program inside our logic. So we need in a sense, a stateful logic. And the way that we embed state into our logic is using these user-defined resources. Before giving you an example of that, let me take a dive into step indexing and invariance and why those are interesting and why those are important. These are the features that actually set Iris apart. One crucial point about Iris invariants is that they are impredicative, meaning that you can create an invariant with any proposition. And that proposition itself may include invariants. And if you're not careful, you can get into trouble with that, right? And indeed, one of the reasons that we have a step indexing in Iris is to avoid paradoxes that could arise out of such nested invariants. But I will not get into any of that here. If you're interested, you can look at Iris papers. Another reason why these two features of Iris are quite important and unique is that they allow us to define logical relations models for quite expressive programming languages. Let me tell you what I mean by that, and let me first say what logical relations are. Let's say that we want to prove type safety for an expressive programming language with references and with recursive types and so on. Now, most of you are probably familiar with the syntactic way of using progress and preservation to prove type safety. But here you want to do something different. You want to use the logical relations method. And the idea is that you want to prove by induction on typing derivation that for any well-typed program E of type tau, then the program is in the so-called logical relations for that type. And now if we have that being in the logical relations implies that the program is safe, then we're good, right? We have proven type safety. But let's think about that. What kind of property we need? How do we need to define this logical relations? Well, safety is not going to cut it, unfortunately, right? Because if we know that two programs E1 and E2 are safe, it is not necessarily the case that we can use them to build a bigger program. For example, if E1 and E2 are safe, there is no reason that E1 minus E2 is safe, right? For example, true is safe, it's a value, right? So is 3, but true minus 3 is not safe. It's not a value, and we don't know how to execute this program. So it's a stock expression. Turns out what you need to do is you need to say not only that your program is correct, but you need to say that the end result that you get out of it is going to be something that is a valid value for your type, right? Now, the question is, how do we define a predicate that describes valid values of a type? Ideally, we should be able to define it by induction on types, right? It is, well, for the type of integer, it's very simple. The values of integers are just numbers. For a product, we can say, well, a value is a value of a product type if it is a pair, and the first element v1 of the pair is in the first type, and the second element is in the second type, right? Everything works out until we get to recursive types, right? Intuitively, what we want to say is that a value of a recursive type is a folded value, fold W, such that the value of W itself is in the type tau, where we have replaced X with the same predicate that we are trying to define, right? But after all, this is the meaning of recursive types, right? It should be defined in a recursive way. But this definition is not well-founded. It's not something that we can do by induction. So you're stuck. Also for references, what is the value of a reference? The value of a reference should be a location that always stores a value of the correct type, right? Whenever we read it, we need to be sure that we read a value of the right type, and whenever we write to it, well, we have to guarantee that we write the value of the right type, right? But how do we express these things? Well, it should not come as a surprise after me hyping Iris up so much. We use Iris, right? The idea is that we use the Hoare triples of Iris to define our logical relations. Remember that this actually implies the safety and the correctness, functional correctness property that we wanted, right? The key point is that we can also define what it means to be a value of a type directly as an inductive definition in Iris, right? Let's see how we define the value relation for the recursive types and for references. Well, for recursive types, as I said, we need to take a fixed point, right? And this is exactly what we do. We use Iris's guarded recursion. In Iris, we know that if we define a predicate over some variable r, such that the variable r is guarded in the sense that all occurrences of r, here they are here, all the occurrences of r in this formula, they all occur under a later modality. And if that is the case, we are guaranteed that we can take the fixed point of this predicate and the fixed point will just work, right? Now let's see what this relation actually says. It says that a value v is a value of the recursive type if it is a fold of a w, and we have that after taking a step of computation, then w is also in the is a value of type tau, where x is actually the same definition that we are defining right now, right? So it is again the recursive type. The only caveat here is that we have that w is a value of the right type after one step of computation, but that is fine if you're familiar with how the operational semantics is usually defined for recursive types. The only way we can get out a value w is by unfolding, and that takes a step. Similarly for references, well, we can say that the value of a reference should be a location, but now we can use Iris invariance to say that something should always hold. The value of a reference, the location should always have a value that is a value of the right type, always. And notice that this predicate here that we have defined may itself include some invariants, and that is why we need higher order and impredicated invariants. Okay, now just to give you an idea of what the difference is, here is a logical logical relations that is defined for an expressive language with recursive types and polymorphism and references. And here on the other side is a language with the same level of expressivity that is defined in Iris. And these red parts here are the Iris-specific constructs that we have used, and that makes things much simpler. And also using this logical relation and proving the properties that you want to prove about this logical relation in order to conclude type safety, those are also that much easier and that much more compact when you work in Iris. This approach to type safety using logical relations is called semantic type safety. It is a powerful approach, and one of the advantages is that it allows you to reason about a combination of well-typed programs and untyped programs. It has, for example, been used to prove properties of the encapsulation properties of the Rust type system. If you're interested to know more, you can take a look at the keynote talk at POPL 2018 by Derek Dreyer. Okay. Let us take a look now at a couple of small examples of verifying a small concurrent program in Iris and see how we can use those ideas of invariants and user-defined resources. Here is a very simple program. It creates a reference with initial value 0 and then adds 1 to it in one thread and 2 in the other thread. And then after the 2 threads end, it reads the value of the reference. Here the fetch and add operation, the FAA operation, is an atomic operation that adds the given value to the given reference. And it is important that this operation is atomic. I will get to that. The property that you want to prove here about this program is what we're going to get at the end when we read the reference is going to be a negative number, right? And that makes sense. We started with 0 and we only added some positive integers to it. So it should be non-negative at the end, right? But how do we do that? How do we prove this property? If you think about it, after allocating the reference, we get the exclusive ownership of the reference. But then we have to kind of share it between these 2 threads. And this is an exclusive ownership. We cannot really duplicate it, right? So we have to actually use an invariant to say how this reference should be used by the different threads and different parts of the program that share it. What should that invariant be? Well, let's take the property that you want to prove, that the value of C should always be non-negative. And that is exactly what we do. Here is the proof. It's a bit too big, but let's go through it step by step. After allocating the reference, we get that we get the ownership of the reference, and at that point we know that the value of the reference is non-negative. And at that point we can create an invariant. We can announce that we want this property to hold forever. And by doing so, we get an invariant that says, well, the value of the reference is non-negative. And this allows us to verify the program intuitively because, well, the 2 threads here uphold this invariant. They only add to the value of C. And also, when at the end we read the location C, we know by the invariant that it is going to have something non-negative. And that is exactly what we want. One crucial thing here is that in order to access invariants, we need some conditions. Here, this is important that the programs, that the parts of the program that are accessing the invariant are atomic. And what I mean by accessing the invariant is that we get that before executing this part of the program, we know that the invariant holds. right? Not that the invariant holds, sorry, that the predicate that the invariant enforces holds. So we actually get the ownership of the location before executing this operation. And we have to guarantee it afterwards. Now it is important that this operation is atomic, because if it were not the case, if we allowed non-atomic operations to access invariants, then it could be that two threads would be scheduled in such a way that they are both using the same invariant at the same time. And if one of them is violating the invariant for the duration of that operation, then the other thread will get into trouble, right? And that is why
I have a
yes.
small question, Amin, which is
Yes.
powered by Zoom in the sense that there is this, black band on the bottom that actually turned the x greater or equal to 0 into a x strictly greater than 0 on my screen. And that specification is also correct, but your proof doesn't work for it.
Yes, that is a very good point. Yes,
and my
indeed.
question was, how would you change the proof if you wanted to prove that at the end, actually, x is positive, strictly?
Well, that's a good question. Maybe the next example that you will see is going to be very close to what you want, or at least I hope. So maybe let's go to that. Let's go to the next example. What if, for the same program, we want to prove that the end result is exactly 3, right? After all, it should be the case, right? We start with 0. In one thread, we add 1, and the other thread, we add 2, right? So at the end, the value should be 3. But how can we prove that, right? This is the same problem that I'm going to explain here now is going to happen as well if we were to try to do what Gabriel suggested and prove that it is strictly greater than 0. But let's see. Well, unfortunately, just using invariance is not going to cut it, right? The invariant that we had before, for example, doesn't work, right? Because when we read the location here, the only information that we have is that the value is non-negative. That is not going to help us with proving that it is exactly 3, right? So we need our invariant, we need some information so that at the end when we access the invariant, we know that the value is 3, right? On the other hand, we cannot just say it as an invariant that the value should be 3, because it doesn't hold at the beginning where we want to create the invariant, right? And of course, it's not upheld by the other threads, even if it were true at the beginning, right? So what we need here is some user-defined theory. We need to add something to Iris. We need to use that idea of adding a state to our logic, right? To be able to track the changes that are happening in different threads. And this is exactly what we do. I will not explain what PCM we actually use, but trust me, we can set up a PCM that gives us that allows us to define these predicates in our logic. Here I'm adding 3 predicates to my logic using user-defined resources. One is sum, the other is left and right, and each of these are tracking a number in the state of our logic, right? If we call it a state. And the idea is that the values that are tracked by the left and right predicates always add up to the value that is stored in sum. This is something that holds by the way that we have defined our PCM, but by the way that we have defined our resource. Also, we get out of our theory that at the beginning, we can allocate this resource, which tells us that we have a new instance of a resource for which we have sum is 0, left is 0, and right is 0. Notice how we are using the update modality. The thing is that this proposition does not hold. We have to allocate it. We have to change something for this to hold. And that's why we need this update modality. But the point is that the program logic, as I said, is defined in such a way that you can always perform updates to your resources to do basically anything that you want in your proof, as long as your resources allow it, of course. Here, our resources must uphold this property, of course, that the sum of the left and right should be exactly the value sum. And the updates that we get out of this theory is that we can always add to the value of sum if we add it also to the left part or the right part. This keeps the sum balanced and everything is fine. And of course, for doing that, we need to manipulate resources, therefore the update modality. Okay, let's see how we actually use this theory that we just defined to prove the property that we want, to prove that we get at the end the value 3. Here is the proof. Let's go through it step by step. Again, at the beginning, we allocate the reference and we get that the reference is initially 0. But after that, at that point, we can also allocate our user-defined resources to get sum 0, that left is 0 and right is 0. And we can use the sum now to define this invariant that says that the reference C should always have a value that is tracked in resources in our logic estate as the sum of the two parts left and right. Notice that here we have put the points to proposition inside an invariant, right? But unlike before, we haven't lost information about it. Before, by putting it in an invariant, the only thing we knew about it was that it has a non-negative value. But now, here, we can actually prove that the value is still 0, because the value is the sum, and sum should be the sum of left and right, and we know that that is 0, right? And now the idea is that we give the left part to the left thread and the right part to the right thread. And the idea is that they can use because they can update the left part or the right part independently when updating the sum, then they can keep up the invariant. We have a question?
Yes. Hi, I mean, just a quick question on notation. Perhaps I missed this. Could you explain again what x dot means?
X dot here, for example?
Yes, and in the two threads above.
Yes. The idea is that this is a binder for the return value. So at the end, the value that you're going to get, if we name it x, should satisfy this property. Right, so x should be 3, exactly. And in this case, the return value is not really important. So it doesn't really appear in the post condition. All right, as I was saying, by giving the left part and right part to the left and right thread, we're actually allowing them to update resources to keep up the invariant. Now, if let's focus on thread the left thread, the right thread is similar. Now, when we access the invariant, we know that the value of C is sum n, right? And that we have sum n exactly. And we have left 0. After adding 1 to the value of C, now we get n plus 1. The only way that we can reestablish the invariant is to actually also update the sum, the value that is stored in sum, right? And the way that we can do that is by updating the left value as well, right? If we go back and look at the rules that we had, we can update the sum if we update also the left part and add the same value to both of them, or for the right part. This ensures that we keep up the property that we want, that the sum of left and right is exactly sum. Okay, what we get at the end is that the two threads, they basically tell us how much they have added to our reference. The left thread gives us left 1, and the right thread gives us right 2. And at the end, what we know is that the invariant holds. Of course, the invariant always holds. And we know that the value for the left part is 1, and for the right part, it's 2. And therefore, when we access the invariant, we know that the value that is stored in C is going to be exactly 3. And that allows us to conclude the proof. Okay. The proofs that I just showed you, I was a bit fast with them. I didn't really give you all of the details. I didn't go through all the rules, exactly how we use formally the proof rules to derive these proofs. And that works. But when we work in COC in a formal system, then we have to follow all the rules, right? However, Iris has a so-called Iris proof mode, which is an interactive proof mode that allows you to reason inside Iris as though you're working in COC itself, right? That makes life much easier. You don't have to actually refer to individual rules and construct proof trees or anything like that. To actually give you an idea, here in this screenshot of my Emacs, you can see a proof of the properties that I just showed you done completely in COC. Here on the left, we have a proof that the program returns a non-negative number. And on the right, we have a proof that the program returns exactly 3. All right. I hope that in this talk, I have interested you in learning more about Iris and program verification in general. If you're interested, there are tutorial materials and Iris publications on the Iris website. I encourage you to take a look at that. And also, these slides are available on my personal webpage. With this, I thank you for your attention and leave you with a list of events related to Iris that are taking place this week at POPL. Thank you.
Thank you. Do we have questions? So we are slightly late, but let's take one or two quick questions if you have them. Sophia, I'm going to make you a presenter so that you can set your screen share at the same time.
Yeah, I don't see any questions.
I should stop, probably.
Perhaps it's best to move on to the next.
Can I ask a quick one?
Yes.
On slide 7, you had an invariant over a specification of a stack, and you said if phi holds for x and phi's for all the values in the stack, and you said this is a list of properties rather than a property for the complete stack. How do I see that this is a list rather than one for the complete stack? Because it's called phi s or what?
You're asking about my notation, I guess. Or
I thought that what you wrote there was Iris code, and therefore that if you wrote that in Iris, it would automatically deduce that phi s is a list of predicates and not one predicate for the complete list.
No. In that case, if you're working in COC, for example, COC will infer this because the predicate is a stack, takes the argument that it takes is a list of predicates. But yeah, okay. Here I'm not exactly, yeah. Here I wasn't writing the types exactly everywhere. That would be too big to fit on the screen.